Welcome to today's lecture. The subject is physics, and we'll be looking at photoelectricity. Photoelectricity. The word photo here means light. Electricity means the ejection of electron. So it means that we're saying light causes electrons to be ejected from the surface of a metal. This effect is referred to as photoelectricity. What then is photoelectricity? Photoelectricity is the emission of electrons from the surface of a metal when light, that is electromagnetic radiation of sufficiently high frequency, shines on it, that is on the metal. When light of sufficiently high frequency shines on the metal, electrons are ejected, electrons are emitted. Now, for electrons to be emitted, the frequency of the incident radiation, that is the light that shines on the surface of the metal, that is the frequency of the light shining on the surface of the metal, must be greater than a certain frequency called the threshold frequency. We can also look at this from another angle, that is the wavelength of the light shining on the metal must be shorter than a certain wavelength called the threshold wavelength. We have made mention of two important terms here. The first term, threshold frequency. The second term, threshold wavelength. We will discuss this later. Let's try to see what we have just done. For light, that is for electrons to be ejected from the surface of the metal, the frequency of the light shining on the metal must be greater than the threshold frequency of the metal, or the wavelength of the light shining on the metal must be shorter than the threshold wavelength. So we can now say that the frequency of the incident radiation must be greater than the threshold frequency, or the wavelength of the incident radiation must be shorter than the threshold wavelength. This phenomenon is called the photoelectric effect, and it supports the particle nature of light. The particle nature of light. We're going to take that topic some other time, the particle nature of light. This aspect of physics was discovered by Heinrich Hertz in 1887, explained by Albert Einstein in 1905 by using quantum theory. We're also going to discuss quantum theory later. Number two, we're looking at key terms and definitions. In other words, terms that will help us understand what photoelectric effect is. The first term we want to look at here is photoelectrons. Photoelectrons. Electrons emitted from a metal surface due to incident light, that is due to the light that is shining on the surface of the metal. The second term here is photon energy, and the symbol for photon energy, I want you to take note of that, is capital letter E. Photon energy is the amount of energy carried by a single particle, that is quantum of light or quantum of electromagnetic radiation. It is given as E is HF. HF. I need you to commit this formula to your memory. Note that the energy of a photon is directly proportional to the frequency of the radiation. That is, the photon energy is proportional to the frequency of the incident radiation. Recall that the speed of electromagnetic radiation is the wavelength of the radiation multiplied by its frequency. So if we make F subject of the formula, we have C over the wavelength called lambda. If we now integrate this into the original formula, we'll now come up with E is hc over lambda, where E is photon energy measured in joules, H is Planck's constant, and the value is given as 6.63 times 10 to the power minus 34 joules second. F is frequency of radiation measured in hertz. C is speed of light or electromagnetic radiation, and it is given as 3.0 times 10 to the power 8 meter per second. Lambda, that's wavelength of the photon measured in meters. The next term we want to look at is work function. Work function. The symbol for work function is W naught. We're using W naught for this lecture to represent work function. What then is work function? Work function is the minimum energy required to remove, eject an electron from the surface of a metal. That is, work function is the least amount of energy needed for an electron to escape from a metal surface. Okay, so it is given by this W naught, which is work function, is Planck's constant H multiplied by the threshold frequency. Also, C is lambda naught F naught. So making F naught subject of the formula, we have C over lambda naught. Lambda naught, that's threshold frequency. So we integrate this into the original formula, we have W naught is Hc over lambda naught. Again, W naught is work function measured in joules. H is Planck's constant, and the value for that is 6.63 times 10 to the power minus 34 joules second. F naught as threshold frequency measured in hertz. Lambda naught is threshold wavelength measured in meter. So write the meter there, measured in meter. Then we have C, which is the speed of electromagnetic radiation, given as 3.0 times 10 to the power 8 meter per second. I want you to note the following, that each metal has its own work function. That is, each metal has its own work function. Number 2, low work function metals emit electrons easily. That is, the lower the work function of the metal, the more easily it emits electrons. For electrons to be ejected, the photon energy must be greater than the work function. That is, the frequency of the incident radiation must be greater than the threshold frequency, or the wavelength of the incident radiation must be shorter than the threshold wavelength. Now, part of the photon energy is used to overcome the work function of the metal. The remaining energy becomes the energy of the emitted electron. This will take us to threshold frequency. Threshold frequency, that's F naught, threshold frequency. This is the minimum frequency of light required to cause photoelectric emission from a given metal. That is, threshold frequency is the minimum frequency required to eject an electron from the surface of a metal without giving the electron kinetic energy. We will continue this topic in part 2.